All right, to introduce evolution population graphs, I want to first remind us, go over in evolution. When we're talking about evolution in nature, what is changing? What changes in evolution? We can have a species change, all right? And it will become a new species. All right, that process is actually called speciation, okay? When one species evolves into a new species. One thing that's changing is a population, okay? The population changes. The traits and characteristics and attributes in the population changes, not the individuals. The individuals are born as they are. They're not changing. It's the population that's changing, okay? Also the genetics. The genetics within that population are changing. So we would say that the gene pool is changing. A gene pool is a collection of, within a population, all of the genes that are available. Every individual in the population, the genes they have are part of the gene pool, the genes that are available for the next generation, okay? That's a gene pool. So the things that are changing, it's not the individuals, it's the population. Changes in the genetics resulting in new species, that's evolution. Most traits have a spectrum. So if I were to take everybody in this school and line them up from the shortest person all the way up to the very tallest person, it's not, we have this very slow, gradual change from person to person to person to person to person, from slow to tall, okay? We don't have just short people and tall people. It's not just like one or the other. Usually there's kind of this slow scale, a range, okay? We call that a spectrum. In any spectrum, we expect on one extreme, so like height, there's going to be very, very few short people. There's going to be some people that are short, but they're like really, really, really short people. There's just a few, okay? Just like on the other extreme, the really, 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 really tall people, there's just a few of them. Most people are within just a few inches of each other. Most people, when you set them next to each other, there's just a few inches of difference. The average, most people are that average, okay, height. Maybe a little bit tall, a little bit shorter, but the average. This is what we call a normal distribution. We get this nice curve shape to the graph when we do this, okay? When we graph out a physical attribute. All right, so we're gonna go through some examples. Normal phenotype distribution of beetle color. So we have light, super light green beetles, a slightly darker, our medium green shades here of beetle, and then a dark green, and then like the super dark green beetle, okay? Population, I've got 10 in the population that are super dark green, and 10 in the population that are super light green. Only a few have the extreme phenotypes. The majority of the population, the 100, 150, 100, the majority of the population is right there in the middle of the spectrum, okay? So if we take this and we graph it, okay? So we have over here on the side population. So we've got, of these light green, we've only got 10. Of this slightly darker, this nearing medium green, we've got 50. Okay, that's that normal distribution. Very few at the extremes, the majority are in the average, middle. Okay, if I were to line graph that, we get that curve to it. Now, if there's a change in the population, this is a population with normal distribution. What if there's a change? What if there's a change in the environment that causes a change in that population? So, scenario 1, directional selection. We have in this scenario a disease. that kills the dark green plants. The environment's changing. Dark green plants destroyed. All right? Now it's the dark green beetles. They're easier for the predators to see. That's not good. Being a dark green beetle is a bad thing. They can no longer camouflage. Not able to camouflage. This is bad. All right? It's also bad. It's bad for your dark green beetles. They can't camouflage anymore. They have no way of hiding. So, if they can't hide, they get eaten. Predators come in, and the original population, after a few generations of them getting eaten first, we have no more left of those really dark ones. We only have a few of that, like, kind of dark ones. These guys kind of got the disadvantage as well, so that number might go down a little bit. This number is still pretty stable, okay? This number probably has increased a little bit. Graphing it, okay? These, they're gone. There's nothing there to graph. Right here, just a few. These guys, which were 100, they're not up to 100 anymore. They kind of were at the disadvantage there. Okay? These numbers probably stayed pretty similar. So we get a shift in that graph. That was where it originally was, but now we have that graph has shifted over. Okay? That graph has shifted over. That's what we call directional selection. Okay? So here we have our original population, that was the dotted line. And then because of the loss of dark plants, the population shifted this way. There's no dark green ones. There's just a few of those dark ones there. These numbers all shifted. Now being a lighter green beetle is a better thing. Okay? So that's what we call directional selection. New scenario. We're going to look at the number of eggs a bird lays at a time. Okay? So in a given year, the bird's going to lay eggs. The number of eggs, we call that the clutch. All right? The size of the clutch. So some birds don't lay any eggs at all. Others, just 1 egg. A few others, 2 eggs, 3 eggs, 4, 5, 6. Okay? The different sizes of clutch. How many eggs get laid and are taken care of together. So, normal distribution, okay? That's what we expect to see happen. We would see a normal distribution of how many birds. All right, very few lay 0, very few lay 0, very few lay 6. The majority right there about in the middle. Now, this is called a stabilizing distribution. Let's analyze. How well do the eggs incubate? What does incubate mean? In incubation, we have the mummy bird, and I'm not doing a very good job drawing, but here we go. All right, there's mommy bird. I know, I'm not good at this. Mommy bird sits on the eggs and keeps the eggs warm. She's incubating them. They need to stay warm so they can have a chance to develop, okay? If she's got 1, 2, 3 eggs, this is no problem. Those eggs are gonna stay nice and roasty, toasty, warm. 4 eggs she can do. 5 eggs, there's a few too many. She's not that big. Like, as much as she wants to, like, cover all of them, she's not going to be able to fit on all of the eggs at a time. I'm sorry, that's just a really bad drawing, but hey. All right? She can only fit on, like, 4 eggs at a time. And so over here, I mean, that's really bad. All right? Some of those eggs will never even hatch because they didn't get enough incubation. They didn't stay warm enough, long enough. So a lot of those won't even hatch because she like sits on 4 and then kind of like moves over and sits on these and then kind of moves over and sits on these. And she just can't keep them all warm at the same time. So that's really bad news for those. The rest of them are, these not very good. Like some of them, I would expect a few of those aren't going to hatch either. I'd be really worried about that clutch of 6. A lot of them I don't think are going to hatch. Okay? How well do the chicks eat? if they all by chance happen to hatch, how do they eat? How do baby birds eat? The mom brings them food. Mommy flies off, finds some sort of like worm or something, brings it back. Okay? She actually like digests a little bit first and then like vomits it back up in the mouth. It's kind of gross. But anyways, all right? So when it comes to feeding, this baby bird, wow, he is going to be one chubby little baby bird. He gets all the food to himself. Okay? These guys, pretty happy and healthy too. These guys, happy and healthy. There's plenty of food for babies, for mom. Right here, if she's got 4 babies, mom's going to be a little bit stressed trying to feed all 4 babies. Right here, if any of them happen to survive to actually hatching, I don't expect, right here, none of them are going to hatch. There's just too many, all right? Right here, if she's got 5 babies, mom's going to die trying to feed them all. Her flying back and forth and going for food, and then she's never going to rest. Mom's going to die. And that means all the babies are going to die too. The genetics that cause the mom to lay 6 eggs, whatever gene or whatever that causes her to lay 6 eggs, all of her babies that have that gene, they all died. So they're not going to pass that gene on for laying 6 eggs. Here, they might, if one happens to survive, it might pass on that gene, but I'm not expecting that gene to get passed on. Okay? Just like right here, a mom that doesn't lay any eggs is not going to pass the gene on where she doesn't lay any eggs to any offspring. There's not going to be any offspring to pass that gene on. How much space is there for the chicks to grow? So we've already know that these guys are going to die anyways. 4 babies. If all 4 babies hatch and they all start growing, mom's able to feed them and they get bigger and bigger and bigger and bigger, they're not going to fit in the nest anymore. All it's going to take is one bird baby go, oh, move out of the way, and boop, and woo, out of the nest falls the baby and it's gone. If it can't fly yet, it's dinner for some other animal on the ground. Okay? So that's kind of risky having that many babies, because once they get bigger, there's going to be the risk of falling out of the nest. Right here, 3, they could probably, by the time they're big enough, they'll probably be able to fly out of the nest before they bump each other out, but the possibility exists. With the others, there's plenty of space. Even if the chicks survive long enough to leave the nest, is that a guarantee that they will be parents one day? No. This is just getting them to be, this is just getting past childhood, all right? Long enough to leave the nest, that's just being childhood. Reproductive success, what could prevent them from one day having the chance to have their own babies? So let's say I'm the mama bird for this baby. He got well fed. I was healthy and happy because I just had one little baby to take care of. He just grew up so great. And now he's a nice big bird and he flies away from the nest. And as he's flying away in, boom, sweeps an eagle and eats my baby boy. My only child is gone. Okay? Predators. Disease. Anything that, just because they survived the nest doesn't mean that they've survived life. They're just getting started. They just survived the beginning. We still have to put in the risk factor of what possibility there is that they'll survive. So if I look at this from the perspective of how many of my kids are going to one day be parents themselves, my chance of being a grandma bird, all right? The odds are low that this one egg actually survives to adulthood to pass on my mama bird genes. All right, this, well, I have a slightly better chance because at least there's 2 kids. Like, hopefully one of the 2 survived to pass on my genes. Right here, we got some pretty good odds, all right? Of my 3 babies, I'm pretty darn sure one of them's gonna survive, at least to pass on my genes, possibly 2, okay? Right here, I've got really good odds of those genes getting passed on. Out of 4 kids, I'm pretty confident 2 of them are gonna survive, okay? 50% chance of survival. We already know that those all are already dead. We take all of these things into consideration. All right? What do we expect is going to happen to our population? So the birds that lay no eggs, those genes aren't going to be passed on. The birds that lay just one egg, that population is going to decrease. How many of those birds that laid one egg, their child is going to actually have babies? That number is going to go down from 50 down to like 10. Okay? Over here on this end, again, none of those are going to survive. None of those babies that have the gene to lay 6 eggs are going to survive. Right here, very few of those that lay 5 eggs. I mean, that's just, the odds of survival are low. Okay? The 4 eggs, not bad. Okay, so that 100, it's not the greatest, but maybe, all right? 2, okay, how many of your kids are going to survive? Well, again, maybe not the greatest numbers, but the possibility is there. 3 eggs, the ideal clutch size. That population will increase. We turn that into a line graph, and we compare that to the original curve. It's changed shape, okay? This is called a stabilizing selection. We focus more in on what is the norm, the average, okay? So we have that selection, and that graph gets more narrow. We focus, this is the ideal. That is the best possible option, okay? This is just not gonna happen, all right? This isn't gonna happen. So that stabilizing selection, okay? All right, next example, we're gonna go back to the beetles. So we start with the normal phenotype distribution. A storm destroys all of the trees. The trees are gone. All that's left behind is dark soil and small dark green shrubs and rocks with light green lichens. So we've got dark plants and dark soil, and we've got light green lichens. Who's going to have difficulty camouflaging? The ones in the middle? It's looking bad for them. There's no more trees left, and the trees is where they used to camouflage. Okay? So these population numbers are going to go down. Whereas these, overall in the population, we expect those to go up. All right? So these numbers, that 50 drops down to 20. The 100 drops down to 30. Okay? That 50, we'll say it goes up to 60. The 10, we'll say it goes up to 20. Okay? So those numbers are going to adjust to that new environment. So when we graph this, these numbers are low, much lower than they were before. These numbers increase, and so do these numbers. So we have a significant drop here, okay? So that original distribution, this population dropped. So did these. They couldn't camouflage anymore. But these were able to camouflage really well, and so those numbers went up. We end up getting a new shape altogether of the graph. We end up with 2 separate groups with a gap in the middle. So 2 separate peaks with a gap in the middle. Okay? We call this a disruptive or a destabilizing selection. So this is the paper you need for this. First, go through the PowerPoint so you have an idea what's going on, and then cut this out, dotted lines. First thing we need to know is phenotype. So phenotype is the physical traits or appearance of an individual. Okay, your phenotype. An organism's physical appearance and their traits is determined by what? All right. Is determined by what we call genotype, which are the genes. The genes, the genetics of the individual. Most phenotypes, not all, but most phenotypes have a spectrum, all right, or a range of variety. So the reality of like hair color. You don't just have people with black hair and blonde hair in the world. There's a bunch of different shades of hair, bunch of variety. And you can put it in a spectrum from like white all the way to black, and you can get some variety in there. Same with eye color. There's a whole bunch of different eye color, and there's not like distinctively just like brown eyes, black eyes, and blue eyes. No, there's a spectrum, there's variety, okay? So most phenotypes have a spectrum or a variety in that population. Normal phenotype distribution. In most large populations, so lots and lots and lots, large population, specific phenotype will have a spectrum of variety. A spectrum of variety. That means there's not just tall and short people in the world. There's tall and a bunch of different types of mediums, okay? There's a spectrum of variety. The distribution usually has a few individuals at one extreme and a few individuals at the other extreme. But most of the population has a phenotype between the two extremes. So that spectrum, just a few people are really, really short, just a few people are really, really tall. So number of people, height, majority of people are right there in the middle, okay? Height is a really good example of normal distribution. So normal phenotype distribution. This is what we expect it to look like. And this is as a bar graph and as a line graph. We have the three different types of changes, okay? How populations can change due to some sort of change in their environment. In a disruptive selection, both extreme phenotypes are more fit than those in the middle. So when we're looking at a normal distribution, the extremes, okay, these ends over here, these are the good parts. These are the good traits now, okay? Because they're more fit. Okay, remember that means more likely to survive. The extreme phenotypes are the ones that are more likely to survive. Okay, so back to examples of beetles. If beetles move into a new environment that have patches of light green moss and has dark green shrubs, both light and dark beetles might be better hidden and therefore survive better than the medium green beetles. All right, diversifying selection makes multiple peaks in the curve. Which graph is it? Is it this one? Is it this one? Or is it that one? Last graph, right there. Okay? This is what we call a disruptive, or it can be called diversifying. So with your colors, all right, our original population, our normal distribution. The extremes are the good traits, and the middle, beetles that are medium green, they're not happy beetles because they can't camouflage very well. After the selection, we'll have fewer medium green beetles, and we will increase the population of the darker and the lighter green beetles. In directional selection, one of the extreme phenotypes is more fit than all the other phenotypes. Okay? So again, more fit, more likely to survive. The beetle population moves into a new environment with dark soil and dark vegetation. Dark green beetles are better hidden, survive better than medium or light beetles. So dark green beetle is good, medium not so good, light, really bad. The directional selection shifts the curve towards the favorable phenotype. Okay, which kind of graph is that? This one right here, a directional selection. So original population, and then after the selection, so in this selection, this was the ideal phenotype, this was the very bad phenotype, this wasn't a very good phenotype either, that was the best. So the population, we're going to get a lot more of those, a lot less of those, and we will probably end up without any over here at the very light green end. Finally, we have stabilizing selection. We can already guess which graph goes with that. The stabilizing selection, the intermediate phenotypes, okay, the ones in the middle, are more fit than the extreme ones, okay, more likely to survive. So the medium green beetles might be best camouflaged and thus survive the best. On a forest floor covered by medium green plants, stabilizing selection tends to narrow the curve. Stabilizing selection. Our original population had that normal curve shape to it, but because dark green and light green means your dinner, all right, being on the extreme ends is not a good thing. Being right in the middle is a great thing. More of them survive, passing on that trait. Stabilizing selection, more of the population, even more of the population is at the center, even fewer are at the extremes. Glue them with their pairs, so make sure you match each graph with its pair. Okay, so that normal phenotype distribution, kind of looking back at that graph, you see on all three graphs, the same color, we colored the original population, that normal. So go ahead with that same color. Okay, that normal distribution, we see that on each graph, so we can see how it changed. The blue was the change. So remember, evolution is about a change in the population. The population changed. These are graphs of that population, and we can see how that population changed. Okay? So go ahead, glue them in their pairs. So glue in each description paired with its graph. And that's the graphs on natural selection. Okay, population graphs for natural selection.